sklearnmetricspairwiseadditivechi2kernel. Description: the additive chi-squared kernel is a popular kernel function used in machine learning for measuring the similarity between two samples. It is particularly well suited for categorical data, such as text documents or images represented as histograms. Inputs: X, a NumPy array or sparse matrix representing the first set of samples. Each row corresponds to a sample, and each column represents a feature. The values in X should be non-negative integers. Y, a NumPy array or sparse matrix representing the second set of samples. The shape of Y should be compatible with X, meaning that the number of columns in X and Y should be the same. Outputs: kernel matrix, a NumPy array representing the pairwise kernel values between all samples in X and Y. The element at row I, column j of the kernel matrix represents the similarity between the ith sample in X and the jth sample in Y. Steps: calculate the sum of squared differences between the corresponding elements of each pair of samples. Divide each sum of squared differences by the sum of the corresponding elements. Take the exponential of the negative of the result to obtain the kernel value. Metrics: accuracy measures the proportion of correctly classified samples. Precision measures the proportion of correctly predicted positive samples among all samples predicted as positive. Recall measures the proportion of correctly predicted positive samples among all actual positive samples. F1 score a harmonic mean of precision and recall. Visualization plots: heat map visualizes the kernel matrix, highlighting areas of high similarity. Scatter plot visualizes the relationship between the samples in X and Y, colored according to their kernel values. Fine-tune parameters: none. This kernel does not have any fine-tune parameters. Uncertainty methods: none. This kernel does not have any built-in uncertainty methods. Challenges and fixes. Challenge 1: data sparsity. When dealing with sparse data, the additive chi-squared kernel can result in overly optimistic similarity scores, as it ignores the zero-valued features. Sample use case: a text classification task with documents represented as bag of words vectors, where most features have zero values. Fixes to challenge 1: consider using alternative kernels, such as the linear kernel, which account for sparsity. Pre-process the data by removing features with very low frequencies. Challenge 2: high dimensionality in high-dimensional spaces. The additive chi-squared kernel can become computationally expensive, as the number of pairwise comparisons grows quadratically with the number of samples. Sample use case: image classification with high-resolution images, where each pixel represents a feature. Fixes to challenge 2: utilize dimensionality reduction techniques, such as principal component analysis (PCA), to reduce the number of features. Employ efficient kernel approximations, such as the Nystrom method.